just to kind of set the scene, a horse monitor probably sounds like you get quite a few people go, well, what horse monitor, how does that work? So in simple terms, as you'll hear me talk in a minute, it's basically it's the Fitbit for the horse world, if you will. The aim this morning really is not to do too much in depth about the horse element, although it's got there's some interesting pieces in there. I probably ought to explain how this talk came about, and it actually goes back to January. So very briefly, I was having a conversation with Judy, and doesn't she do a great job?
Yes.
And so we're having a chat, and she said, hey Richard, you know, what are you working on at the moment? I said, oh, you know, doing this horse tracker. She said, what do you mean horse tracker? So I said, well, yeah, you know, it's like a Fitbit for horses. She's like, what? Well, you know. So the conversation went on a bit more, and it's like, well, why don't you do a talk about it? Okay. So it's as much as anything else, it's a kind of a moniker around, you know, it's an interesting project. It's been quite a learning curve, because the first thing you have to remember is what I knew when I started working on this project about horses was you give them sugar lumps and the rest of it I can write on a postage stamp. It's that much. So that then brought in a whole raft of learning. I'll give you a quick bit of background about me. I'm not going to go through any of that lot. That's just for background. There's probably, if any, thread out of that, the first thing I have to stress is I am not an RF engineer. Need to be really clear about that. I am not an RF engineer. However, as you'll probably see from that brief, I'd probably be better described as a baseband engineer. I've butted up amongst a whole variety of basebands, probably since the early 90s, generally CDMA, sometimes GSM. So for those people who've enjoyed Rick, who I'm delighted to see this morning, and Mike's presentations, there's some great old hot topics about how you connect up converters and things like that. So anyway, we'll move on from that lot. It's quite scary when you write it down, really. So the first thing is, what's this tracker thing, you know? It's like, how do you put it on a horse? Good question. So where do you put it? So basically, and none of this was anything to do with me, I hasten to add, there's a harness. This is actually not actually attached, but eventually you end up with a device down between the forelegs of the horse, and there's a girth strap, and in fact I think you can probably just see it there. That's actually a wireless heart rate monitor. It's actually outside of the scope of this project. It's a piece of proprietary technology, because as you can imagine, trying to put a heart rate monitor on a horse's wrist is, well, it's not going to stay there very long, is it really? So this is really where it started, and there was a conversation involved a startup incubator in London. And just to give, by way of just a quick bit of background, I'm not going to go through these in detail because they're really not my area of expertise, but these are just some of the things that the device does. So that's everything from movement, heart rate. It does, you know, some of the interesting one. There's the interesting one. You know, is the horse staying in a particular place in the field? Is it trying to get out the gate? So there's a whole bunch of analytics which is completely outside of scope of the hardware, but quite fascinating nonetheless. Got a couple of stragglers there. Needless to say, it's an IoT product. Where does the data go? Into the cloud. So that then gets transferred to where else? Your mobile phone. Which, if you think about it, it's quite a novel concept. I mean, you know, I was kind of, you know, first introduced to the project. It's like, sorry, let me get this straight. You've got a horse in a field. You can walk around. You can be anywhere in the world, and you can look on your phone. Oh, how's my horse doing? Well, for me, that's quite an interesting concept. So, delighted to say that our customer has got this on trial with a variety of veterinary partners, notably obviously the Royal Veterinary College back in the UK. And there's a whole bunch of other people who are trialing the technology. So, the obvious thing is, how do you start the design? Well, as we'll come on to in a minute, I should explain actually this particular startup Trachiner have achieved what I personally think is a pretty amazing amount of work for what amounts to be in most people's parlance, a very small engineering team. The core team when I met them were 3 people. 2 very, very talented French founders, and Pauline Issard and Jeremy Charlet, and what they'd achieved with another engineer from Poland, so it's quite a multinational team, and they'd actually already done a proof of concept, which we'll talk about in a minute. But the first and obvious thing was just in terms of putting a device on a horse and getting it down small enough but robustly enough to actually go on a horse. And we'll come on to the robust bit a bit later. But one of the first things is, as with most startups, you need money. So of course the first thing is, how do you actually get somebody to envisage what it is? And don't worry, because 1 or 2 faces in the room, the kind of reaction that I saw this morning is not the first time I've seen it. So yeah, usually the first thing is, well, what is this thing? Where does it go? So one of the things one of our first briefs actually was just that, was to come up with this, okay, you want to do this tracking device, how on earth are you going to put it on a horse? So that involved a mixture of MCAD and ECAD, and we came up with some visualizations. One of the first ones then was, well, okay, what are we going to do about an antenna? Is that something that's going to lend itself easily? We can just pop that on we can just simply put a ceramic antenna on a board, or do we do a patch? And of course it's got GPS in it. So one of the next things then was to start building some candidate components into libraries. No, I didn't say circuits. At this point we just literally looked at what kind of components we've got to put in this thing, and let's have a look at what sort of materials we're likely to need to use. And ironically, we probably did more in the mechanical area than we did in the electrical, because an awful lot of this was just, where do we go from here? So where did we start? So the design, the PCB up on the screen, in fact, was originally done by one of the team at Trachiner in Circuit Studio, which was actually quite a big bonus for us, because obviously it meant that we'd already got a reasonable starting position. We could pull that into Altium. We could at least use some of it as a starting point, because clearly some of the key components like the cellular modem, we didn't then have to kind of go out and select. Some of that already existed. This large black device, that's actually the heart rate receiver. So, all right, there was a bit of work to do there, but the bottom line was we'd at least got a starting point. But very sensibly, the team at Trachiner had decided that they weren't going to get into any significant RF engineering at a proof of concept stage. Incredibly sensible. So they simply said, okay, we'll put some RF connectors on the side, we'll put a couple of off-the-shelf antennas on, and hey, we can get ourselves going. There were some trade-offs. They had a few sensitivity issues, etc., etc. But as a proof of concept, it got them started, it went in an off-the-shelf box, and they were at least to get a basic idea. But one of the things that came up was it was lithium battery powered. Now, I'm sure most of us have all seen the various headlines around lithium battery technology, and I don't know if anybody else knows, but the horse world is a bit more than just your daughter's pony down in the field to some equine racecourse that couldn't be worth several millions or more in value. So one of the first conversations that came up was, well, lithium's very nice, but if it goes wrong, if anything goes wrong, and if there is any kind of mechanical distress to that lithium battery pack, it's it's not a conversation you want to have with a serious horse owner, or certainly one with an expensive horse. So one of the first things we started to do was say, well, actually, we're not keen on lithium. There's a whole bunch of other reasons we'll come on to later on the regulatory side, but maybe we should go for something slightly less exciting. It's a trade-off. Okay, there's a good reason we use lithium. It's very, very good for density, but obviously it comes with some risk. So I'm afraid we went back to, for those of us who remember back far enough to the early days of GSM cell phones, we went back to good old nickel metal hydride. It actually has a couple of other benefits. One of the great ones is the negative terminal is the outer case. Now, of course, lithium's the opposite way around. So at least one of the other benefits you've got is that all of the positive, the energy part, is any of this sounding familiar, is inside effectively the can of the battery. So that actually gave us some benefits. And then we went and looked for a battery holder and things like that. But because of the space requirement of trying to get this device down between the forelegs and to fit the harness, which had already been designed, there was then the question of, okay, so we've now got some issues around where do the antennas go, and we've now got this nice big chunk of metal that sits over the circuit board. Excellent. Just what you want if you want to create a reflector. So we did some concepts, and I should explain there aren't any circuits behind these boards. This was literally, early stage, pre, any significant investment. These were literally hand-placed components, just to be able to get that initial feel of where's this design going. So one of the first things we established was that we needed to, so this white area in fact was basically, as we described there, that was it, as it were, the starting point location of there will be an F-type antenna to do cellular there somewhere, and we'll figure out the exact details. I hasten to add the antenna design is done by a colleague of mine, so detailed questions on antenna design, don't direct them at me. One of the other challenges you've got, and this is a common problem with most IoT product, is as soon as you start putting a cellular module with any form of GPS, you now need to make sure there's a significant loss between the two, because otherwise, inevitably, you're going to find that you're going to deafen that GPS receiver fairly quickly. And not just when the GPS transceiver is turned on. Even if you power it down, you've got to have some loss between these two antennas, and that's partly around some of the reasons for the separation of the antenna and some of the trade-offs. So we did some more work, and needless to say, of course, there was the inevitable mechanical work in SolidWorks. But as you can see fairly quickly, you've now got this basically metal barrel, the actual plastic, the battery holder itself is plastic, but you've now got this metal barrel that is now sitting over the circuit board with two antennas on it. So that created some challenges, and one of the things that my colleague did, we started to look into, okay, how does that load the antenna? Because we all know, as Rick explained so well in his presentations, as soon as you start putting anything above a trace on a board, whether it's solder mask, conformal coating, and even better, you go and put something nice and conductive, you've now just changed completely the field dispersal around that board. So we'll come on to some more detail on that, but that was at least to give an idea of where we started. One of the other things I should explain, the original design was USB charged. And of course the only problem with that was that's great, but of course you'd have to kind of go out periodically, go out to the horse, take the device off the horse, take it home, plug in into a USB port, because for some strange reason they don't put USB ports in fields that horses are in. I can't understand why. So that was the other reason for the replaceable battery, and obviously the other advantage of nickel metal hydride comes in a nice convenient AA size cell. So then there was the usual, okay, we could do with running something up quickly, we're on a tight budget, right, where's the 3D printer? So we started creating some mock-ups. So in fact the top left one gives you an idea of printing in action. The initial material, in fact, we used for 3D was just simply to run them out in ABS because at least that gave us something to start with. What we also learned, unsurprisingly, of course, is that that type of material is great for getting forms together, but obviously structurally it doesn't work. It doesn't work so well. So we ended up. So forgive me, I'm going to do that live demo thing, and this will probably go horribly wrong, but we'll give it a try. So we ended up, and this is, for anybody who's worked in some of the other CAD systems, this is where, I have to say, having done other odd, funky form factors, it's not, sorry, it's just, I've got to do, is it going to get me across? Yes. No. I knew this was a bad idea. Okay. So if you'll just forgive me a second.
Do you have to take it out of presentation mode?
Yeah, I think you're right, Rick. I think we're gonna. Yeah, I'm just gonna have to. Right. Okay. Not ideal, but it'll do. So I won't float it around too much, but as we saw in the previous, in fact, in the keynote this morning, you know, these obviously it's the usual. No secrets how this was done. So obviously there's the step export from Altium. This was in fact done in SolidWorks, but it just again just gives that reinforcement of just how good Altium is at this kind of thing. I hasten to add we've been doing this for a while, albeit the flow is a lot simpler, and I'd love to get to the kind of slickness we saw earlier. But you start to get an idea of the problem. When the battery's out, we've got this nice big spring. Okay, we don't have to worry about that too much because obviously it's compressed when the battery's actually inserted. But even so, we've now got a compressed spring plus the battery sat right over a cellular antenna. That sounds good. And as we'll come on to a little bit later, we've got to start thinking about where the GPS is going to fit. So let's see if we can do this without. Oh, that's a new one. I've got an Altium slide deck in a ECAD drawing. That's quite new. Okay, let's get rid of that. Okay. So, by way of a slight digression, the other inevitable one that always crops up, regulatory. Touched upon it a little bit with battery safety, but of course we're now doing a radio product. So whether you're in North America and you worry about FCC, or whether you're in the EU and you worry about CE and the Radio Equipment Directive, you've got to think about them. And you've got to worry about battery safety standards. One of the other reasons that we encouraged in this particular case to go away from lithium, for anybody who doesn't know or hasn't been involved with lithium product, it comes under the dangerous goods regulations, otherwise known as a UN regulation. It's completely global, UN 38.3. And what that basically means is, depending on the amount of lithium content in the battery, that can mean anything from, if you're really lucky and you've got a small lithium polymer cell in a product, you may well find you can just pop one or two devices in a box and you can send it to somebody. But as soon as any of the lithium content, or particularly if you've got smaller devices but you want to start mass shipping them, suddenly you move into the whole world of UN 38.3 and dangerous good regulations. Well, that doesn't sound that bad. Is it a bit of paperwork? Well, no, unfortunately it's not. You get into just very quickly, there's a bunch of things. The first one is, typically for any company that does this, they have to have somebody who actually understands the dangerous good regulations and will have to issue things like packing instructions. So that's literally how the product goes in the shipping carton. And that isn't just something that you read in a book or look on Google. You've actually got to go to a course and you have to get accredited for it. There's obviously then a whole bunch of other things, because then when you start dealing with carriers, you've got to go through all that kind of paperwork. So the lithium has quite a long tail. The other point about it is, and this is one, if you're even contemplating doing lithium, choose your battery supplier and your cell supplier very carefully, because there are plenty of vendors out there. We won't talk about where in the world, but there are plenty of vendors out there who will tell you, we will do you a very good price on a cell or a pack. And then you have to ask the inevitable question, yes, but is it certified? And it's not unusual to have the answer, you want certification? Yeah, that's extra. That's another $15,000. So, and the thing to remember is that you have to certify the pack. So even if you've bought the cells, and your manufacturer is putting them into some sort of pack, and I should explain, the cells are just that, they're the battery cells. But if you're not familiar with lithium, there's what's called the protection circuits. So there's things like, there's typically a thermistor which is brought out on a third pin. There's things like short circuit protection, there's deep discharge protection, so if the cell is taken too low, there's typically a MOSFET, the protection circuit gets switched off. But all of that has to be certified. So the moment, even if you take a certified cell, there's a bunch of certification around that, even if you take a certified cell and you put it in some form of pack, then you've got to certify it. And it's one of those, I'm sure for all the folks in the room who are involved with automotive, that means even if you take a pack that already exists, that your manufacturer is already making, and you want to change the connector, guess what? You've got to recertify it. All right? Some of the scope is smaller, but you've still got to recertify it. You want to change the wire length, different part number, you've got to recertify it. So, and the thing to keep in mind with that is typically it's not quick. So, and I speak here for, a number of customers had the shock, right, okay, yeah, but we do need to change the pack slightly. And then there's that unpleasant shock of, if you're lucky and your vendor's really good, it might be 8 weeks. But if you're unlucky, you could be talking about 38.3 testing can take anything up to 3 months. So just to and the other thing to keep in mind is we go, we'll carry on prototyping before the pack arrives. Yeah, but you're now handling uncertified products. So all of those early product you've got, you can't even take those near standard dangerous goods, for example. That kind of product has to go in stainless steel fireproof containers. And particularly if this is where a really good vendor earns their money. We were doing early trials, not in fact with this customer, a different customer. And they were the ones where, they work there, because there are issues with early low volume packs if they're pre-production. And that's where having a vendor, particularly if you're working in Western Europe, so I'm assuming everybody is, having that vendor who can say, hey, you've hit a problem, don't worry, we'll go to your manufacturer and collect the pack. Okay, great. We haven't got to get rid of, what is uncertified product. So, the other thing to keep in mind on the regulatory side is you've got a software or a firmware team, they're all furiously coding away, but remember you may need, depending on what radio technology you're using, and if you've been through this you'll know, you may well need some custom software to actually put the modem in the way that it expects. I won't go through this particular slide. I'm sure the slides will be made available afterwards. This is actually from a white paper I was involved with. It talks about selecting wireless solutions, and it's between whether you go and buy the module that happens to be $2 or $3 more, or you're going to take the RF chipset and lay it out yourself. And there's a whole bunch of pros and cons. I don't want to go into that. But let's go on to designing antennas and RF into products. And one of the first questions we often ask when people come to us and they go, hey, we're going to put RF traces, or we're going to put an antenna on a board. My usual question is, so what material do you want to use? And I get this great answer, which is FR4. And usually my answer is, that's nice. So, for those who don't know, courtesy Wikipedia, FR4 is it's a flame retardant class. There's a multitude of materials out there. DK anything from 2.5, 4.5, 4.9. And the other thing you have to remember is, typically most manufacturers specify it, particularly standard FR4, what do they specify it at? 100 megs. That's good. Ah, yeah. The radio's working at either 850, 900 megs, or anything up to 2.1 gigs. So,
The east of R is spec'd at 1 megahertz.
yeah, depends on them. Yeah, exactly. I mean, certainly, I think from memory, Panasonic used to spec at 100, but you're right. You know, often it's an LF measurement. So this is where you want to understand, what's the DK going to do over the frequency range of interest? And that can be anything from, I mean, FR4, yeah, okay, to be honest, anything over about 2.5, 3 gigs, you probably ought to be looking for a different material anyway. And just to give some perspective, I mean, I was working alongside a radio team in the mid-90s where on L-band radios, as they were termed then, about 1.5 gigs, we were working on things like G-Tech. We were working with controlled material. And if you wanted to do a 3.9 gig radio, hey, guess what? You did it on Teflon. So it tells you just how far we've come in terms of being able to put chips on boards on what are relatively run-of-the-mill materials and actually get, I mean, to be honest, it's even a miracle that we can get anything to work beyond a gig on materials that, let's face it, FR4, it was defined in 68. So to be honest, it's even a wonder it even works. And of course, one of the reasons is because everything's got sufficiently small enough that the feature sizes are enough that we can start contemplating these kind of things. But the other thing that often we've seen is people tend to select their pregs and their pre-preg thicknesses based on what they do for the digital domain. And unfortunately, they're two different things. As Rick explains in far more detail than I will in his EMI course, the digital guys, most of the time, they're just simply, it's small feature size, they've got big BGAs, they want small traces, they'll go for one in terms of aspect ratio, trace to height. Great, don't have to worry about loss. But the radio guys do. And one of the things you have to keep in mind, particularly on the radio side, because it's analog, remember those sine wave things? Or for those of us who remember in the 90s, a lot of digital engineers were like, what are you doing about analog? It's all ones and zeros. It's like, yeah, have you actually looked at the signals on the backplane? So the thing to keep in mind here, we saw an example of this in another design. In fact, it was on a LoRaWAN type product, where again a substrate had been chosen that was quite a bit thinner. It was far more like a digital stack-up, and there were some issues and a user story. So you need to think about the thicknesses, and often they're quite a lot thicker. So whereas you're talking in the 100 micron type for a digital board, it's not unusual. Typically you'll start at 250 micron and you'll normally go a fair way higher. A quick digression: if you're in this scenario, was in this with a particular base station product where you end up with a mixed signal board, you've got RF and digital, then it's not unusual, because the RF guys like to put their components and do most of their routing on the top. So it's not unusual that you'll have a plane that will exist in the digital domain, typically layer 2, it's got a fairly thin substrate, but you will just simply chop that out in the RF area, and then there will be an inner layer 3 or 4 perhaps, which will be that much thicker, so you can maintain that increased thickness. So I'm covering a little bit of this, but one of the things that we often say to people is, and the real point about that FR4 question is, normally with a digital board, if you've come up with a class of material and you've got a reasonable stab at it, you can normally say to somebody, hey, go into production with that. And as long as the materials are reasonably representative, if somebody switches the material out, it's not a major issue. within reason. The problem with RF designs, we talked earlier about the regulatory piece. So the problem you've got with your PCB is it's now a critical component in your regulatory story. It's a traceable component. So when you need either you're big enough and you've got a big purchasing department, they say, hey, we want to go and buy whatever the laminate is because it's so much cheaper. Or you're a smaller organisation, you've perhaps prototyped somewhere in Western Europe or in North America, and you're now doing the classic thing, you want to move it to a low-cost production site somewhere else in the world. You need to think almost in reverse. Start with the material you intend to go to production on. So this is where Mike, for example, Mike Crichton and I have had conversations. His one is, and there's an awful lot in what he says, which is you start off with a high-performance material for prototyping. Prove the design. Don't try and don't end up tripping yourself up because you've used a poor material. My experience, which is involved consumer and high volume, think about the material you want to end up on. And that can be a challenge because sometimes you'll find that laminates that are available in Southeast Asia may not be available in Western Europe. Been through that one a few times. But particularly if you can engage with your mass production manufacturer, and that's both fab, talk to the laminate vendors. It's great, we've got laminate vendors outside. Ventec in particular should get a special mention. We found them particularly helpful. Not just because obviously, sourcing in Southeast Asia for Ventec is no problem, but they have excellent technical support in Europe. So that's another one to keep in mind, is not just about the choice of material, but can you get it prototyped in Europe, and can you get the support for it? So in Ventec's case, for example, we talked about, okay, so what's the decay at a particular frequency? And the great thing is Ventec characterised their FR4 materials across a big frequency range. So that makes your life an awful lot easier when you start to plan out how you're going to lay your product out. So I'm sure you all do this, but apart from the stack-up on a radio board, we would strongly recommend that you write a printed a formal specification. Talk about what the specific traces, feeders, anything like that. Put it in a formal specification. What we tend to do is have an iteration. We don't keep a polar field solver in house. We don't have that kind of budget, but a couple of our PCB manufacturers do. So we will work with them. We come up with a set of geometries. They'll give us a screenshot of the polar results. We will now embed that in that specification. So the big advantage then is, providing you've chosen a laminate that is available in your area of low-cost manufacturing, and perhaps you've done the conversation with your local lower volume initial trial vendor, the great advantage is by the time you've verified those first prototypes or early builds, your engineering trials, you have a fully documented stack, and you can then have a far more meaningful conversation with that low-cost manufacturer. And what we've tended to find, certainly with a couple of major EMSs, as soon as you start delivering things, documents like that, rather than just embedded in the Gerber data, the manufacturer views the board differently. And it's partly a contractual thing because you're providing a formal specification, not just some stuff that's tucked on the side of some design data. So very quickly, I'm mindful of time, so I'm not going to go through the details. As I say, I'm not an antenna designer, but just to give people a flavour, this was an L-shaped antenna, so we could support the various frequencies of GPS and GLONASS. And the way we did this, the classic one, RF engineer sketches up the features in DXF, and then we import them and create the symbols. And we did the same with the cellular antenna. We'll come on to some of the details on that one in a minute. So where did we end up with? So we ended up with, as you can see with this one, we've got the F-type antenna there. The GNSS antenna, as you can see, now tucks to the one side of battery holder. So the obvious question was, so how did you test it? So we ended up making very sexy jigs with 3D printers. They're great, aren't they, for just knocking things up quickly. But what this allowed us to do, as you can see, is it allows us to place the battery holder in the this in fact was the very early antenna proving platform. And I'm sure you've all seen our RF engineers attacking bits of copper-clad board with a scalpel. Well, that's exactly what that is. So, but the point was that was able to get my colleague in the right kind of ballpark. And then obviously as we got a board, we were then able to do some similar level tests. This was also very helpful for doing the matching work. So just by way of explanation, that's the matching network there. And then, as one always has to do, we then went and did some field tests. So this is, just for clarity, this, for those who've not been involved with this is not EMC testing. This is where you go into an RF chamber and you're actually doing a scan around the device to look at the propagation pattern of the antennas. So this was the device actually on the table, and you can see we brought the feeders out through the side. And then you end up with these rather nice donut type patterns, and I have to say we were actually really pleased with the plots.
But when you place the device underneath the horse, that's more or less a big water tank.
Yep.
And that will
Of course.
interfere big time, right? Yeah.
It will have an impact, but it's like all these things. You know, there comes a point of you can only, you know, but you. I mean, we could have done more work, but one of the difficulties is horses vary a lot. I'll come back on that one in a minute if I may.
But you've got a decent DOP for your GPS signal underneath the horse.
Yep.
Okay.
So very quickly, we ended up with a couple of versions of the board. Probably there aren't that many changes. I'm not expecting anybody to do the eye test spot. Probably the major one was the usual story. You'll notice that we didn't actually put the ground shunt on the cellular antenna. That went on Rev 2 once we'd done some more testing. I'm going to speed up a little bit because I'm mindful of time. We also did some PDN analysis. I won't go through those in detail, but suffice to say, obviously the main one is the transmit path is obviously the major power consumer. And again, we did some PDN analysis on this just to make sure that we weren't, obviously I stressed, this is DC analysis, just to be clear, it's PDN DC analysis. So obviously we are expecting the decouplers in the cellular area to deal with all the HF paths, because if we don't, we've got some serious problems. But what we are interested in is, for those who've not worked with things like GSM, you can see current pulses of 2.5 amps on the supply rail, and we obviously wanted to make sure it's a battery powered product. We want to make sure we're not just basically warming the board up instead of putting power in the transmitter.
You were doing a DCIR analysis.
Yes, exactly. Just this one's a quick aside at manufacturability. If anybody isn't aware that you can do it, obviously we had to put in various test points for mass production, and there's the useful feature which you can set up is if you are putting test beds down, then you can just pop a rule in to make sure that you meet the component pitch, the test pad pitch that your manufacturer uses. So in terms of trials, this is where we found out about tolerancing. So the obvious question was, okay, how big is this horse? Because I stressed this was only 1 or 2. Majority of devices all went out, happy days, no problem. But there were 1 or 2, and then suddenly then you get into this rather interesting measurement called hands. I still don't actually understand what it means, but all I do know is that anything over about 15 hands is a big horse. That's probably the extent of my knowledge. So we had to look at this. And this is where we found out about tolerances. Ah, okay, that's quite a big tolerance. So we obviously had to do some stress analysis. which was done by another of my colleagues. So, and we identified the fact that, in fact, the LED light pipe hole was, in fact, one of the major culprits and was the stress concentrator in the sidewall of the gates. So it's not actually that easy to see, but we did some work around that area and then did some re-simulations to improve the sidewall strength. So very quickly, some of the things, Altium's great for producing proof of concepts at any stage of a device. If you've got a small team, you've got an investor. But I would even say in bigger organisations, and I've done this in larger organisations, sometimes when you're trying to engage product teams, being able to put together just very simple conceptual PCBs that can be put together with some mechanics can be a really great way of getting people to help people visualise things. Understand the materials. Can't stress that one enough. Anything to do with an IoT device that's involving wireless, you really must understand the materials you're using. IR drops, particularly with battery powered product. Let's face it, at the end of the day, what is the biggest thing that's going to help you with battery life? Making sure that whatever comes out of the battery is given to assist the RF get the signal out. Because if you start wasting energy, and there's plenty of ways to waste energy in an IoT device, that's a good one. Understand the regulatory piece just very quickly. It's all right. This product was fairly straightforward. It's a single radio technology. For those who are familiar with the ETSI standards around the Radio Equipment Directive, as soon as you put more than one radio technology in, transmit, I hasten to add, you can't use the pre-compliance declarations of the modules or subsystems you're using. So if you want to put Wi-Fi and cellular together, or DSRC, or any number of other ones, be aware of the fact that all of that testing that your module vendor has done to prove the protocols and all of the radio performance parameters, you will have to go through again in the case of a multiple radio scenario. You can't rely on the pre-compliance. And lastly, there's a little bit more background. There's a white paper that I was involved with recently. It's free. It's freely available, downloadable from that link. And that just goes into more of some of the end-to-end of taking a product. Its context is for scale-ups and startups. I'd like to think there's still some meat in there for people who work for larger organisations, because its focus is about understand the life cycle model of a hardware product from that first sketch to what it takes to go to mass production. It doesn't do everything in depth. It's, as I found when I was involved with writing it, it becomes a big subject. But hopefully it'll give some pointers. And lastly, I'd like to say a very big thank you to our customer Tracker for allowing us to share some of the details of the design. As you know, normally when you're involved with supporting customers and designing their products, they prefer it if you don't say too much about their design. So we're very indebted to Tracker for allowing us to do so. So at this point, I'm going to open up the floor. We're probably a little bit overrun, but I'm happy to take questions if people want to stay for a minute or two. Rick?
Yeah, you said you need to understand the materials when you're dealing with antennas. I assume you mean not just board materials, but all materials, packaging and everything.
Correct.
Because of losses?
Yes.
Yeah.
What comes back to the conversation that was taking place the other day about, as Happy was saying, if you go and conformally coat a board, you've just changed the dielectric. So, and that's obviously why we did when we were doing the characterization testing. And to the gentleman's excellent question here about, you need to you've got to understand all of the things that go around the product.
And as he pointed out, the horse is a serious loss factor.
Yeah.
Yeah, you're really there you go, good plan.
Gentleman, full throwback.
Right, thanks, Richard. That's a nice talk. I got a question about the power budget. You did quite a good screenshot on the PDN side, but since you got two different RF signal in their cellular and GPS, so how did you manage to get a decent power budget with respect to such limited battery size?
Oh, it's a great question. It's kind of you're almost asking the generic conundrum to most IoT devices. Probably the simple answer is there's obviously a variety of things. They work off different switch mode power supplies. So you get involved a lot with worrying about the efficiency of power supplies. But one of the ones we've seen a number of times that catches people out. People tend to worry about the efficiency of the DC-DC converters when everything's switched on, which is great, because if you look at most converters at whatever their intended load is, you'll usually find, the manufacturer does its best. Hey, it's 92, 95%. Problem is, when you put the device to sleep, and particularly with some microcontrollers, you could be talking about deep below the milliamp mark. In some cases, you're down into even sub 100 microamps. The problem at that point is you suddenly find that an awful lot of DC-DC converters, if you've ever looked at the curve, it's kind of, it can drop. I mean, to the point where you can be talking about, I've seen figures as low as 40%. So suddenly what you see is you've put the micro to sleep and you've done some other stuff and all the rest of it, and then suddenly you find that actually what's happened is the device hasn't gone to that deep low power mode that you thought it had gone, because all that's happened is instead of dissipating the power in the micro, you're now dissipating the power in the switcher. So that's a definite one to keep in mind. Some of it involves firmware, which we weren't directly involved with. I hasten to add, Tracker handle that themselves. But there's certainly, again, one of the pieces of advice we would give people is, as hardware engineers, we like to pride ourselves in meeting a specification and developing a piece of hardware that will do these things. But you also need to communicate that to the firmware team, because often what you'll find is that it's not firmware team. They're a clever bunch of people, but they won't always understand the nuances around particularly partial powering of devices. It's okay if you can put the additional buffers in, that when certain parts of the subsystem shut down, that those buses will go tri-state, or they will power down benignly. But often you may not have the space, you may be bomb constrained, and you can't put those buffers in. So one of the favourite ones we see is things like, that serial port, when you want to go to sleep, you're actually going to have to deinitialize that serial port and disconnect the GPIO, because otherwise you may end up back powering part of the circuit.
We have to wrap. Unfortunately, we're out of time.
Okay, Rick, I'll happily take up.
Yeah, if you wanted to stay after, I'm sure that would be fine. We'll give the speaker. But this is one of the last chances to get anything from the Altium store. This is one of the last chances to check out the sponsors in the foyer, and it's lunch, and followed by the keynote speaker. I know that the first keynote got on a little bit late, but we have to stay on schedule. I'm so sorry.
All right.
No problem. Thank you.
Comment on the switch mode power supply, if I may. When you're looking for a switcher, the controller itself, if you see a note anywhere in their data sheets or app that says add a snubber here or there, run like hell. Because what they're telling you is our supply won't pass EMI testing without this snubber. And if you put the snubber in, the efficiency is going to go from 96% to about 70%. You're going to kill the efficiency of that supply with that snubber. Be aware of that.
Yeah, that's a really great comment, Nick. Absolutely, Rick. We've just had that, actually not on an IoT product, but on a motorboard, on a different project, and exactly that problem.
Yeah, I've seen that a million times. It's aggravating as hell. You have to really look hard for a switch mode supply.
So I'm going to, if you're happy to stay, I'm happy to take questions.
You mentioned that you use USB to charge the device.
That was on the proof of concept. On the later version, it's just simply the insertion of the AA cells. But we have done USB type powered devices.
I'm not sure if the hose will go outside. Is there a waterproof problem?
Yeah, that, to be honest, that was actually one of the reasons. That was another reason why we went to having the sealed replaceable battery pack for that reason, because some of the problems around USB and the fact you're now taking a device that's been on a horse and you want to bring it into a some kind of domestic environment to charge it. So that was actually one of the reasons why the USB interface was dropped from the proof of concept. Okay.
Excellent job. Really well.
Thank you very much indeed. Thank you for staying.